So the fundamental theorem of calculus is the connection between derivative and area, which is what made it kind of a large body of work. I mean, when you get past calculus in math, it kind of branches out. Sometimes, matter of fact, mathematics is kind of described as a tree. Arithmetic is kind of the trunk, and then algebra is a little farther up the trunk, but everything comes from there. Geometry in there a little bit, then the connections between that, and then calculus, and then from there it branches out. And so you major mathematics, then you start branching out into all these other little aspects that have some algebra in them, have some calculus in them, but then they kind of go off on their own. But calculus became an important part of that trunk once those connections were made to that. So when we talk about the invention or the discovery of calculus, it was really about tying together two really separate things that have been worked on and were important in mathematics, but when this connection to them, that they were tied together, was found, that's what made it such kind of a big deal. Okay? So anyway, let's parse this. I think I might have in the video a little bit, but remember, this is the area function, right? And so what this is saying is that the derivative of the area function equals the original function. Well, what does that mean? That means if you take the derivative of something and get this, then that means that thing you took the derivative of is the what of that? The antiderivative, right? I mean, that's how you say something's the antiderivative. Why is 3/2 x squared the antiderivative of 3x? Because when you do the derivative of 3/2 x squared, it gives you 3x, right? That's how you show something's the antiderivative. With derivative, we have rules to follow. Why is x squared's derivative 2x? Because that's the rule. You do that. But for antiderivative, there isn't really a rule. The rule of why something's an antiderivative is because when you do the derivative of it, you get back to what you started. Okay? Well, that's what this is saying in fancy lingo. So this is saying that area is the antiderivative of little f, right? That's what fundamental theorem part 1 is saying in a nutshell. So if you want to write that down, or maybe you did yesterday, that is essentially saying that the area function is the antiderivative, okay? And so we want to carry that forward with us at all times. Every time from here on out, when we are doing a problem and we see an area function, an integral with an x, we want to think to ourselves, oh, that's the antiderivative of whatever little function is inside there. Okay, it's the this thing here is the antiderivative of that little thing in there. That's what we want to think. Okay, but this is a fancy way of saying it. Okay. Notice there's an x in there, right? Because when we do the area function, we use t in here because we're using x for this. But when we do the area function, remember we write it a of x or big F of x or something. And it's with respect to x. So when we get this out here, we're going to have that. Now, I think I also said in the video, I said this. One of the questions that's going to be on the quiz, did I have that in there? One of the questions that's going to be on the quiz is going to be something like this. Yeah, I had some bizarre, but it didn't have an x, it had a t, right? Some weird, bizarre looking thing is going to be like this. And I'm going to give you this, and I'm going to say, and I'm going to ask you, what's the derivative of that? And what's the answer going to be?
E to the 2x.
Don't forget the sign.
Oh, yeah.
Sine e 2x. That's going to be the answer right there. That's all you have to do, right? Now, you can't put a t in that final answer. It's got to have an x in it. But what you're saying there is this little thing in here is little f. The area function is saying do the antiderivative of it. And then this out here is saying then do the derivative of it. It's like the square root of x squared. They're canceling each other out, right? This is saying do the antiderivative of this, but you don't even have to do it because then they're saying then do the derivative of it. Those two things are going to cancel each other out. You just need to get back to what you're left with, except there won't be a t in there. There'll be an x in there. Okay? All right. Does the 2 matter? What was the 2? It was the plus c. So that means when you do the antiderivative of this, it would have a plus c on it. What would happen to the c when you do the derivative? It would just disappear, right? The derivative of constant is just 0. So that's why this doesn't matter. Whatever's down here, if you're doing the derivative of the antiderivative, they're going to cancel each other out. Plus c won't matter. Because when you do the antiderivative, you'll tack on a plus c, you do the derivative of the c will go away. And so it doesn't matter what that is. Okay? All right. So let's talk about that thing we did the other day with the shift real quick. Let's say this was my little f. Let's say this was my little f graph, and I had big F and big G are two different area functions. Let's see if my voice will pick up on the video. All right. Let me have to shout. So here's little f. Now let's go back to chapter 1 right now. What do you care about? Now remember, little f is the derivative of this, right? Of big F, right? Because we know that. This means antiderivative here. So little f's the derivative. So what do I care about on little f here? Up until this point right here. Or better yet, what's this point right here? It's a local max. Positive, negative, positive. So big F's got to go up, down, up, right? Now, don't both of these have to do that? Yeah, they're both antiderivatives. So the only thing we always said is we don't know where to start, right? We need an initial condition, right? We need to know where to start our big F or our big G in this case. Well, I think I said it again in the video yesterday, you get a free initial condition with these, don't you? Okay? What initial condition do we know here with big F? Big F of what?
0 equals 0.
Big F of 0 equals 0. So doesn't that tell me that big F's got to go through there? And what do I know on big G?
Or 2 equals 0.
Big G of 2 equals 0, right? So I know the big G graph has to go through that point right there. So once I know that, then I kind of know the rest of what's going on, right? So the only thing that's going to change, and you can tell, look at my area from 0 to x. If I do the area from 0 to x, aren't I going to have some negative area for a while? I'm going to have some negative area for a while. Well, until there. I'm going to pick up negative area, negative area, negative area. But then all of a sudden I'm going to pick up positive area that's going to start bringing me back up here. And pretty soon I'll have enough positive area to cancel out that negative area. And sure enough, I'll hit 0 again. Right? Okay? And then what about this one? What if I started at 0 on this one? What's this area on this function? Careful now. What's this area right here? Isn't this negative area?
Yeah.
It is. But wait a minute. Aren't I? Because I'm going backwards, right? From 2 to 0. So I'm going backwards. So as I come along here, what I'm actually doing is losing negative areas. So you look at this problem here. Oh, I'm on the wrong one. Dang it. You were wondering that, weren't you? I'm having a rough day today. That's what I get when I take a day off. All right. Right here. So I'm going 0, so 2 to 0. So this is backwards. So what's this area?
Positive.
This is actually positive area. So what's happening is I've got positive area here. Sure enough, positive area at 0. But then I'm losing that positive area. So I'm coming down here to 0. Okay? And I'm losing positive area. And then, all of a sudden, start picking up which would be more positive area, because now I'm not going backwards anymore. So now this is positive area, and so now I'm going back up, right? So I mean, all those things still end up fitting where I need to. Okay, let's look at your homework. I think this was one of your problems, wasn't it? Is this
Yes. This was 14.
14? Yeah, 12 through 14. Let's talk about that. Okay, what time is it? Okay. All right. So on 14, they said that little f was greater than 1. I feel like I'm hearing things now. All right. So maybe we should talk about, well, all of them, I guess 12 through 14.
Yeah.
Explain why big G is equal to big F plus C. Didn't I talk about that in the video? A little bit with the plus C. Because they're both antiderivatives. The only difference is this fixed piece of area between what and what? What's the only difference between these two, area-wise? Well, but it's from 0, and this one starts at 5. So the F graph, yeah, if I put X over here somewhere, right, then the big F graph would be all this area, right? And G would only be this area, right? So the difference between the blue and the red is just that fixed piece of area between 0 and 5, right? So the C value would just be this area right here, right? That's the difference between big F and big G. They're both antiderivatives. It'll just, the C value will change. It'll be this piece of area is the only difference between those two, okay? Now, so that's 12. 13, is big F of 6 greater than or equal to 6? Well, first of all, what do you think of when you think big F of 6?
0 to 6.
It's the area from 0 to 6, right? You put a 6 right there. So the area from 0 to 6 would be over here. Is that going to be more than 6? Why? Because this function's above 1. How much area is right there?
6.
It's, right? I mean, right there is 6. From 0 to 6. And this function has to be above that. So absolutely that area has to be more than 6. It's 6 wide and more than 1 tall. Yes?
How would you explain that on the test?
I would draw this picture, and I would write some words. Well, and some of those words, not just any old words, some of those words would be, that's a great question, because you really can answer this 2 different ways. As a matter of fact, most of the stuff we're talking about, because we've now tied this back to derivative, we can talk about it as area, or we can talk about it as slope, or derivative, chart stuff. Let me give you both of them. The area explanation would be what I just said. This picture, and I say big F of 6 is the area from 0 to 6. Looking at the picture, that would be 6 wide and at least 1 tall. So that's an area of 6, and there has to be at least that or more. And that would do the picture plus those words. But here'd be the other thing you could say. We know that big F is what? Fundamental theorem. It's the one big thing you got to know. Big F is the antiderivative of little f. Now, what's that mean? That means that big F prime is equal to
F.
little f, right? So that's telling me that little f is the derivative, right? This is this speed limit law. The old book called it the racetrack. Well, the first edition of this book called it the racetrack law for some reason. And then changed it to speed limit law, so take it back. The speed limit law is what this is. Think about it. Because big F, when they tell me little f is greater than 1, that's like telling me big F prime is greater than 1. So let's think of this in terms of slopes. So that means the big F slope is more than 1. Right? Now, remember, didn't we say we had a free initial condition here? Big F of what is what? Big F of 0 is 0. So I know, so another way I could have done this was to draw the big F graph. I could have said, I know big F of 0 is 0. And I also know that big F prime, or little f, which is the derivative of big F, is greater than 1. So that means if I go over 6, I have to go up how much? At least 6. So I know, because of slope, I know that big F of 6 has to be at least 6. Isn't that what our speed limit law problems look like? Same exact thing. again, it's kind of cool. All these things are kind of cool. All these connections all the time, right? We can talk about them in there. So I can ask you these same questions that we had before, where we were thinking of slopes. We can now think of them as areas, and they all fit. Talking about that. So I don't care. Either one of those explanations would be fine with me. If you're going to use this one with slope, you got to tie in that this is the antiderivative of that. So that big F prime is little f. Okay, as a matter of fact, I think that's a good thing to write anytime you have one of these area function problems. As soon as you see this, write down that. When we get to the AP test and those problems and they want to justify, part of your justification is you got to make that connection right there. That's the quickest and fastest way to say that something's the antiderivative of something. Big F prime is equal to little f. You're saying right there that big F is the antiderivative. That's what you're saying, without having to write it out for it. Okay? All right. So that's 13. And then 14 was what? Oh, also kind of a racetrack thing. So is big G of 3 bigger than big G of 5? Well, big G of 3 would be the area from 5 to 3. Well, what would the area from 5 to 3? Remember, that's backwards. That'd be negative. And what's big G of 5? 0. So is a negative bigger than a 0? No. So that would be false. Okay. I read that was not 14.
Yeah, 10 is the 10.
Jeez, God, losing it. Sorry. 14. Is it possible that G of 10 is 3? That's what it was. Is it possible that G of 10 is 3? Again, this is a speed limit law, but also area. G of 10 would be the area from 5 to 10. So if you go from 5 over here to 10, that's got to be at least how much? 5. Right? And you know that G of 5 is 0. Right? You know G of 5 is 0. So from 5 to 10, that's got to be at least 5. So could it equal 3? No. Couldn't equal 3. Okay? All right. So those are the things we're wanting to be able to do. So let's move on here. We're going to do this. Or no, this was part of your homework too, wasn't it? 29 through 36. So I don't want to spend, I've already done a bunch of this, so I don't want to spend much time on this because I told you you're not going to have to do this on the quiz, all this stuff. So just trust me, this is like what I just was showing you in the video earlier. We just picked a different function here, 2 minus 3x. So big F would go from 0 to x, so I just put x over here somewhere, so it'd be 2 little triangles, crosses there at 2/3. I just took the function 2 minus 3x, set it equal to 0, and saw that it crossed to 2/3. And then I went down here to h from -2 to x, that'd be way out here, it'd be this triangle out here, plus all the way to there, and then this triangle, okay? And so I kind of wrote them up. I could FOIL them out, whatever. Trust me, it's going to come out 2x minus 3 halves x squared, and then there's going to be some c there, right? It's going to be the antiderivative of this. We know it. It's going to happen, okay? What I care about is all the problems then that come after that, okay? And I think you just use the chart. Just use the chart for them, so don't make them harder than they are. So when we go to number 30, well, you're supposed to find the number c. Well, if you found all these equations, you'll find that, so I'm not going to worry about that. Number 30, find a formula for big F minus big H. Well, what should happen if you take any of these two and subtract them from each other?
Should get C.
The c will just be the only thing left, right? Because that's the only difference. The 2x will subtract out, the -3 halves x squared will subtract out, so not a big deal here. Here's where I really care about from here on out. So 29, 30, 31. So this would be 32. Where is big F increasing? This is little f. Where is big F increasing? From where to where? -infinity to 2/3. Big F is increasing where little f is positive. Right? Why? Because big F and big G and big H are the antiderivative, right? The one main thing you got to know here, big F, big G, big H are all the antiderivative of this. That means this is the derivative of those. So this is a derivative. So big F is increasing whenever little f is positive. -infinity to 2/3. What if that problem would have said big G instead? What if they would have said, where is big G increasing? Same answer. Where is big H increasing? Same answer. It's where little f is positive. Remember, because big F and big G and big H are just vertical shifts, right? Just vertical shifts. So they're increasing at the same places, okay? Where's big F decreasing? From 2/3 to infinity, when little f is negative, right? Yes, I mean, that's the result from this, okay? Is big F concave up anywhere? Well, big F's concave up when little f is, chart. Big F's concave up when little f is increasing. Is this ever increasing? No, so it's not concave up. Is big G concave up anywhere? Is big H? No, same answers, same answers. So they ask about big F, big G, big H, it'd be the same answers. Is big F concave down anywhere? Everywhere. When little f is decreasing, big F is concave down. Okay? So again, the importance of these problems is, since we've figured out the big aha that big F, big G, and big H, the area function is the antiderivative, all the stuff we learned with the chart comes into play.
So when we say like decreasing, you mean like the
Little f graph.
The area is becoming more negative.
Well, it could be either. It could be becoming less positive, or it could be becoming more negative. I mean, if we really want, you don't have to. See, I think to answer this question with the chart. But if you want to talk about it as area, let's do that. Okay? Let's do H, because it'll be easier. So, big H, let's begin to draw it. Now let's do big F. So let me come over here, and let me say I'm going to start to draw a big F graph. Now let's start at 0, because that'll be easier. So let's start to draw a big F graph. Now what point do I know on the big F graph? I know big F of 0 is 0. And then what's going to happen? Now think of sliding, and remember that orange that we had in that thing that I was showing you with the area the other day? So let's start here at 0, and let's slide this way. And I'm going to pick up some area here. Now what kind of area am I going to pick up? Positive area. But what are the chunks like that I'm picking up? Smaller and smaller chunks of positive area. So is this graph going to kind of go up and do that? And level off? Right? And then I'm going to start picking up chunks of what kind of area? Negative. And what kind of chunks? Bigger and bigger chunks. So isn't that graph going to start going down and just go down steeper and steeper and steeper? Right. Now let's come back to 0 and let's slide the other way. Finish my graph. So let's slide this way. So now I'm going to start picking up this area. What kind of area is that? Because I'm going backwards now. So I'm picking up negative area, right? What kind of chunks? Bigger and bigger chunks of negative area. So wouldn't this have to keep doing that right there? Oh, it's an upside down parabola. Is that surprising? No. No. Where's the max at? 2/3. Right? Is that surprising? Where little f went from positive to negative, right? Not surprising. Okay? Concave down everywhere, right? You know what I mean? So area, so yeah, picking up bigger and bigger. So at one point this was negative area and getting more negative, right? Here it was but here it was positive. Here when I picked up some positive area, right? Here when I picked up some negative area, what was happening is my area was positive and getting less positive. And then once I got to here, it was negative and getting more negative, right? So I could go through that. You could go through that reasoning if you want. Heck, that's big F, right? Now let's do on that same grid, let's do big G. Let's do big G. What point do I know on big G? I know G of 1 is 0. So this was 2/3, right? So 1 was right here. So I know G of 1 is 0. Everybody with me on that? So now let's go past that. So let's slide. So let's slide. So this is G of 1. So I'm right here at 1. Right here at 1. And I'm going to start sliding that way. Okay, so I'm picking up some area. What kind of area am I picking up? Negative and bigger chunks, right? So this has got to go down, down, negative, and they're getting bigger and bigger, so it's got to be getting steeper and steeper going down, right? Now let's go back the other way. So I was right here at 1, right? So let's go this way. What am I picking up? I'm going backwards, right? I'm picking up positive area, but what kind of chunks? Smaller and smaller chunks of positive. So it's coming up, 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 smaller and smaller chunks leveling off right there. Oh, same place. Leveling off same place, isn't it? Now what am I picking up? I'm picking up negative chunks. I'm going backwards, so I'm picking up bigger and bigger chunks of negative. So it's coming down, down, down. I don't know where, at some point it'll balance that out. Maybe it's at 0. I don't know. Okay? Isn't it the same graph, just shifted? I kind of slide that over a little bit, but right? But notice the max still happened right there at 2/3, right? Even though the chunks that were negative or positive changed because my left endpoint changed, but it didn't matter. It's still a plus C. Okay? I don't need that, though, to answer these questions. I don't need that. And then 28, of course, says are F, G, and H all antiderivatives? Well, talk about anticlimactic. Yeah. They are. Okay? All right. Let's do this one together. So write in your homework. This is going to be, was this part of your homework? This was not part of your homework, right? So part of tomorrow's homework. Let's just start tomorrow's homework page right here. Let's do this right now. 39 through 44. All right, so again, similar scenario. I'm not even going to do the first part of it. On 39, it says find a formula for the area function. Okay, now this is absolute value. We're not going to do it. It'd be the same thing at triangles, trapezoids, just like what we were talking about there. We know what's going to happen is it's going to come out an antiderivative. Now, the difference is with absolute value, you have to do piecewise because you're going to have two different branches of the V graph, right? But this is basically a V graph shifted where? Up to, and
It's negative absolute value, so it goes down.
so it's going down, and it's a slope of 1, so it'll cross there at 2, and it'll cross over here at -2. Oops. So it's this V graph right here. Okay? So now, and the area function is 0, is starting at 0. Left endpoint is 0, but again, that just affects the C, right? Is all. Now, what I want everybody to understand is how could what's another way I could write this area function? Instead of putting little f of t in here, what else could I write the actual function in here? What would I write? 2 of t dt. So it gave me the function using x, which is fine. Out here, I can write it as an x, but when I put it in there, I got to put a t. Okay, so sometimes you're given the actual function in here. Sometimes they give you the function separately, and they put little f in here. Whatever, doesn't matter. Okay. All right, so here it is. So now let's talk about the question. So I don't care about the formula for it, but let's go to 40. Where is big A increasing? So let's pretend this was the test, and this is number 40. Where is big A increasing? And you're going to say what?
Where's A?
Where is big A, this area function, increasing? This is little f right here.
From -2 to +2.
-2 to +2. Bingo. Be a lot of this on our next quiz. This should be easy. They're just chart questions, like a chapter 1 test all over again. Right? From that standpoint. Be good. Should be good. 41. Where is big A decreasing? Negative infinity, -2, 2 to infinity. And then why? Because that's where little f is negative. Little f, and it would be good here to say, hey, you know what? A prime is equal to little f. It would be really good to have that on our paper. We see that area function, we would say, hey, A prime is the same as little f. So where is A increasing? It's when A prime is positive. Well, A prime is the same as little f. So you really can't talk about A and use F as a rationale if you haven't connected them somehow. So this connects, right? So that should be on your paper, right? A prime is equal to little f. All right. 42. Where is A concave up? A concave up when little f is, when A prime is what? Increasing. So that would be from negative infinity, 0. And then, of course, 43, concave down, would be from 0 to infinity. Right? And then 44. Where does big A have inflection points? Which would be when x is, right? Because we just said concave up from negative infinity to 0, concave down after that. Because this switches from increasing to decreasing, we said that was at local max and mins of f prime, right? Well, in this case, it's local max and mins of A prime, or little f. So right there at x equals 0. Again, so those should be easy, right? We didn't even have to think about area. We didn't think about area. Now we could. Casey asked about that before. And so if we want to say, so if you want to get into that, if you want to say big A, the area graph increasing, you could say, okay, at 0 we have no area. Then we're going to pick up some positive area, but smaller chunks. So it's going to be increasing to there. If we go backwards, this is negative, right? So the graph, the A graph, it, starts here at 0 and goes up. And then it going back the other way, it's going to go down. Well, that's increasing during that time. So from negative 2 to 2. I mean, you can get into that. I think it's really good if that makes sense to you that you could graph that area graph and think about the sliding thing back and forth. But you don't really have to. If you've made this connection about antiderivative, just use our normal chart stuff, right? It's just like you're looking at a derivative graph and they're asking you about the original function, and that's all it is. That's all it is. Okay, let's move on to this. This is also part of your homework, but this one, well, it's going to be like your homework. Let's write this down. So put down a little note to yourself that this is like 61 through 65. You can put it right in your homework. That's fine. What we're going to do right now is very much like 61 through 65, which is going to be part of your homework. Okay? So I'm going to go through this with you, and then that'll make sense, help 61 through 65 make sense. Okay? And it's also leading to the next big piece. You know how we called fundamental theorem, what we wrote down at the beginning of the day, fundamental theorem part 1? Well, why would we call it part 1? If there's not a part 2, right? Or a part 3 or whatever. There is a part 2. There's only 2 parts, promise. And actually, you'll really like part 2. Part 2's a lot easier than part 1 conceptually, and it's actually the more useful of the 2 parts. Of course, without part 1, we couldn't do part 2. But anyway, so here's what we'd like to do. If you think about it, the whole reason we've been getting into this is to do a problem like this. I mean, look at that right there. I mean, this is what we want to be able to do, right? I mean, it wouldn't hurt you to draw a little picture of that right now. This area is why we're doing all this stuff with antiderivative. Because think about how we started. We started this process by trying to find areas, and we stuck with circles and trapezoids and triangles, right? And we did that for a couple days. And that's going to be on the quiz, right? You're going to find some circles and some trapezoids and some triangles and some rectangles. We did that, but then we realized that's pretty limited. How do we find this area? Right? That's what we want to be able to do. So we started investigating, right? And that's where this idea of the area function came in. So we created this thing called the area function, and we realized that it was the antiderivative. Like, oh, okay. So somehow the antiderivative must be involved. So this is what we're going to discover right now. Okay, so now we're going to put it all together. We're going to say, okay, we wanted to be able to do this area right here. And we've now realized that somehow antiderivative must be somehow involved. So we're going to do it. So let's say I had some big F function called this. Notice I got my t squared here, which is like x squared, right? So it'd be the same. Now how come I can put x squared inside on this one? Yeah, there's no x up here. This is just a definite integral, right? This is the fixed piece of area I'm trying to find. But I'm just going to tell you that this thing is called big F right here. Okay, so let me show you how we're going to put this together. Now, the nice thing about this is you're just going to have to do this one time together with me, and then try it again on the homework on 61 through 65, and then we won't ever have to do it again. Okay? Again, it's still valuable. I know you're thinking, well, why are you making us do it? Well,
No.
Seriously, yeah, I don't care. This is good. Yeah, so your stress level's lower. That's good. I'll just write it down and go along. Yes, exactly. You aren't going to have to be able to do all this. Now, the ideas that are behind it and all that, you need to kind of understand those to answer some types of questions, quiz, absolutely, right? But no, when we get done with this and we get our result, we get our part 2 of the fundamental theorem, and I give you this problem, at the end of this, I'll show you what you will do then and how you will use it once you do a quiz. And then that's what we'll spend a lot of Monday practice, okay?
Okay, I just have why did the people who actually thought of this, why did they think of it? What application to life does this have? I'm not.
No, I get you.
I just want
yeah, real quick. The two problems. I think I might have mentioned right at the end of the video.
Right.
The two big things that were happening in the 1600s, Isaac Newton, Galileo, all the mathematicians where this kind of came together. Two of the big scientific type things, or the mathematical type things that they're working on, which seem totally unrelated. One was astronomy and seeing that the Earth was not flat and right and all this stuff. And so a big part of that was telescopes and optics and so forth, right? And what is a key component of optics is refraction and stuff like that. And so if something comes in here at a certain angle, it bounces off at equal angles, but you can't do an angle with a curved surface. So when we talk about refraction, we're talking actually about this angle. Well, look what that line is right there. That's a tangent line to a curve. So when you're dealing with telescopes and optics and things like this and refraction, finding these lines and these slopes and these angles of curved surfaces was a big deal. It was a mathematical problem of the day they had to solve. Well, so that got into rates of change and derivatives a lot. So people were working on that like over here, right? And then another thing was back in the day, think of the 1600s. It wasn't so much money. Who were the rich people in the Middle Ages in the 1600s in those days? Landowners. Landowners were the rich people, right? That's who had the money, were the landowners. So how much land you had, right, was determined how you, and so if you were going to trade or sell or barter or whatever, land, you need to know how much you had. So if I got a river over here, and then a fence here, and then this other guy's property, I got a big grove of trees, whatever, and this is my property, and I need to know what that area is. Figuring out area of curved and odd-shaped surfaces was another difficult problem of the day, right? So these were mathematical issues that were being tackled. In the tackling of those, guys like Isaac Newton and Leibniz and people like that found that there was a connection between these two. And then from that, all these different applications like optimization problems and all these things came about, which made it then become this big deal. So that in a nutshell is why these things got thought of. Okay, make sense? All right. So back to this. So here's what we're going to do. We're going to say I want to do the area from -3 to 4, but all I know is this function that goes from -1 to x. Well, remember the other day we did this, that if I want to do -3 to 4, I could do this plus, tell me what to put here. -1 to 4. Wouldn't this be the same as that? With me? Okay. Now this one doesn't quite look like this because the -1's in the wrong place. So can I flip those two? Could I put the -1 down here? But then wouldn't it be opposite? Okay. And then this one would be this. With me so far, notation-wise? Now what's another name for this? It's got a negative 3 in place of the x. So couldn't I write this as big F of negative 3 with a negative on it? And wouldn't this be big F of 4, correct? Now I don't like that negative there, so I'm going to flip those two. So doesn't it look like this would be the same as that, which is the same as that, which is the same as that, which is the same as that? Are you with me? Right? Now, I know what you're thinking, probably. What good is that? Well, there's a lot of good in that. Because what have we learned about big F? What have we learned about this? It's the antiderivative. Right? So, doesn't this tell me that I could find the antiderivative of this and plug in a 4? Now, it would have a plus C on it, right? The antiderivative would. But wouldn't this one have a plus C and wouldn't this one have the same plus C? So when I subtract them, what would happen? The plus C would go away. It would just subtract out, so it doesn't matter. So really, I could have picked anything for my negative 1 right here. It wouldn't have mattered. And this still would have worked, right? I could have put a 7 there, and I had a 7 there, and then I got my 7 down here, and it would have been the same thing because the plus C would just subtract out. So isn't this telling me that to be able to find this, all I really need to do is do the antiderivative of x squared, which is 1/3 x cubed, and then plug in a 4, and then plug in a 3 negative, and subtract them? Isn't that what that's telling me? Now that I know that the area function is the antiderivative, right? Which, notice the negative 1 ends up not having anything to do with it. It's just that number and that number. Somebody do that on your calculator for me. What's that, 64 thirds? Maybe we don't need calculators. Negative 27 thirds would be, that turned into plus 27 thirds. What's that, 91 thirds? Did I do that right? If that's really true, that's going to be pretty cool. Because integral negative 3 to 4 of x squared well, every year I never know if it's going to work. So it's always a relief when it works. Seem reasonable? 91 thirds? I mean, I guess 30 something, but that's probably go way up high.
Where did you get the 1/3 from again?
Oh, antiderivative of x squared. So we raise the 2 up to a 3. And we'll stick with simple antiderivatives right now. We're going to get some more practice. Part of Monday's homework, or homework for Monday, is this. And then we'll practice more Monday. But we raise that up to a 3 and then divide by 3. So 1/3 x cubed, and then plug in a 4, and then plug in negative 3, and then subtract them. Turns out that's what we do. So in 61 through 65, it's going to be a little bit of this again, this part of it. So Allie, back to what I was saying earlier, this part you're not going to have to do except a few times on the homework. But what we can do is just take the result of what we just saw. The result of what we just saw and what we just learned by going through this whole business with area function, which made us realize that it's really just the antiderivative. The area function is really just antiderivative. What it's telling us is that to do a definite integral that is not a geometric shape, all we have to do is do the antiderivative of this guy, plug in a 4, plug in a negative 3, subtract them, and we got our area. So obviously, it's going to be pretty important to know how to do antiderivatives. So maybe a gateway test or something to practice our antiderivatives. Sorry. We're going to have to know how to do antiderivatives. For this to work, we've got to be able to do the antiderivative of whatever's here. But if we can, see the plus C doesn't matter. We figured out the plus C doesn't matter because when we subtract, we got that. So here we go is fundamental theorem part 2, which is a much simpler conceptually. This part of the fundamental theorem is the part that actually we use. Part 1 is what allowed us to come up with part 2. Part 1 was just, hey, the area function is the antiderivative. Wow. That's cool. You know, that connects area back to slope. Okay. So that's really all part 1 is. Matter of fact, when I was in school, the books we had actually had these reversed. Part 1 and part 2. Okay? So it doesn't really matter. But I think what they were saying is, this is the one you really use most of the time. Right? This is the most useful. But then I think now the thinking is, yeah, but you couldn't even do this if you didn't have part 1. So this should be part 1. Whatever. So it doesn't really matter to me. But all right. So this says if you're doing the integral of some function from a to b, you simply do the antiderivative. That's why the big F. It doesn't matter what antiderivative, because the plus c subtract away. So we just do the antiderivative, forget the plus c, and then we'll subtract them, and there it is. Okay? All right. So to be able to do those, obviously we got to be able to do, remember the one the other day we said the sine, this hump right here from 0 to pi, what did we say that area was? Remember that? It was 2. So the area from 0 to pi of sine x, they told us was 2. Well, let's do it with this new thing we just learned. Fundamental theorem part 2. So fundamental theorem part 2 says what? We do the antiderivative of that. What's the antiderivative of sine? Well, here's how you check. Let's say you thought it was just plain old cosine. Now that's actually the derivative of sine. So you say, how do you check? Take the derivative of it. What's the derivative of cosine? Negative. Oh, okay, so what's this need? Needs a negative. Now if you did the derivative of that, it'd be positive sine, okay? Now, let me show you the notation we're going to use. I call it right bracket notation, or we call it right bracket notation. So what we do is after we take the integral off, a lot of times you'll see books do this. And I think it's good notation to use. I'm not saying you have to write it, but I think it's a good thing. What this tells me is, okay, I've already done the integral, or I've done the antiderivative, so the integral sign is gone. I've done the antiderivative, but I'm going to put this bracket in here to remind me, okay, now I'm going to plug in a pi, and then I'm going to plug in a 0. So it's going to be negative cosine 0. No, excuse me, pi. I just said pi. Negative cosine pi, we put the top number in first, minus negative cosine 0. Right? Well, what's cosine of pi? Cosine of pi, isn't it negative 1? Cosine of pi is over here. That's negative 1. Oh, and you were doing the negative already. I got you. So opposite negative 1, so that'd be 1. Change that to plus. What's cosine of 0? Cosine of 0 is 1. 1 plus 1, 2. Sure enough, that's why that hump there has an area of 2. Okay? Fundamental theorem part 2. We now have a way to do that. So the last thing I would say, and I'm running out of time, so I guess it better be the last thing. So what we've done, and to be honest, we're pretty much done with everything that's going to be on the quiz. There really is nothing new for me to tell you. So Monday is going to be more about putting it all together and that stuff. And you're going to get a lot of practice on most of the concepts. Your homework for Monday is going over really most of the concepts that are on the quiz. Other than you don't have many where you have to do like trapezoids and triangles and stuff. But that's easy stuff. So if I want to do an area, a definite integral, we really have 3 ways we can do it. Okay, we really have 3 ways we can do an area. Right? First would be the way we started at the beginning of the year. We could approximate. Like, remember when we counted squares? Remember that? We would have some area and we would just count squares underneath it, right? So one way would be to just approximate the area. Another way would be geometric formulas, right? If our function with just a line or some sort of a piecewise that just gave us trapezoids and triangles and stuff, we could just use geometric formulas. The first one's not great because it's not exact. The second one is not great because those are pretty limited situations. So of course, best one, the most useful one is this one. FTC part 2. Right? Big F of B minus big F of A. Now, what we will find is that there are some limits to number 3. Well, what would be the obvious limit to number 3? What would allow you to not be able to do number 3? If you can't find an antiderivative. Because you know what? There are some functions that don't have antiderivatives. Right? With derivatives, we have rules. If it looks like this, you do the derivative. So we can always find the derivative. It doesn't find sometimes, but we can find the derivative. But there are functions that don't have an antiderivative formula. So then we'll talk more about approximating. Sometimes that's the best we can do is approximate. But for us right now, we'll be doing ones where we can do the antiderivative. And we'll stay with pretty simple ones for this week. Okay? All right. Oh, homework. Here it is.
Oh, darn it.
Oh, yeah. Oh, darn it. No, this is pretty important homework. For the quiz, which is going to be Tuesday, okay, you need to spend some time with this, right? I mean, this is your most important review. This is your most important review for the quiz. Because what I give you on Monday is not. It's going to be a little bit of extra practice. And to be honest, we might even cover a little bit of new stuff that's not even on the quiz. We'll see how things go. Okay? So we may, it'll probably take about 10 minutes worth of stuff, but the chances are I'm probably going to go over a little bit of stuff that's not, that's going to come after the quiz. So your most important quiz review, and to be honest, if we were looking at a 3-day weekend, we'd probably do the quiz on Monday. But, if this was the next day, we probably would have got ready for the quiz. So, this is key. All right.